All right, everyone. In this video, we are going to track some exam caliber examples going through a number of instances of resonance and how we draw the contributors. Now, before we begin, I think what's important, kind of scrolling back, is that we acknowledge that in some problems, you might begin at the very end of a pi system and then have to resonate across it. Okay. But in other examples, you might begin in the middle and then be able to resonate, to the left or to the right. So I think it's very important, first and foremost, to acknowledge if we're at the end of a pi system or in the middle whenever we start a question. For example, looking at this first structure here on page 5, notice that the carbon of positive charge is adjacent to this pi system and the oxygen atom, so we're technically starting in the middle here. Let's also acknowledge that we're overall positive, and therefore only one arrow is required to go from one contributor to the next. One arrow push that's possible here is delocalizing from the oxygen into that empty p orbital of the carbocation. That would make a pi bond between the oxygen and the carbon, and the rest of the structure would stay the same. As a result of that push, the oxygen would take on that positive formal charge, or just filling that empty p orbital. Now, from that starting structure, we could alternatively do this red arrow push, where I'd go from bond to bond, and that would delocalize the positive charge across the system, moving it in a 1-3 relative fashion to this carbon atom here. Okay, so because we started off in the middle, two different arrow pushes are possible. We can delocalize in blue here, making the pi bond between the oxygen and the carbon, or alternatively, we can use this red arrow, going from bond to bond, moving the positive charge across the system. Then there's one other possible resonance structure. Notice that because the positive charge is directly connected to the nitrogen could use its lone pair to fill that empty p orbital. And as a result of that push, the nitrogen would take on the positive charge, and the rest of the structure would stay the same. All right. And at that point, there's no additional resonance structures because we've exhausted the extent of the pi system. The extent of the pi system is here, and we've used up all available possibilities. Okay. Now, in a later video, we'll talk about resonance structure stability, but please note that on an exam, you might have as part of a question being tasked with drawing all possible resonance structures, and then from there also identifying which one is most stable, which one is least stable, or even ranking them. To briefly overview that, when we look at resonance structure stability, comparing them, we would first look at full octet versus incomplete octet. The ideal would be to have full octet atoms. The carbocation itself is incomplete octet. So these are both really unstable because of the carbon of positive charge having an incomplete octet. When the oxygen resonates into the empty p orbital, that creates a full octet structure. And when the nitrogen resonated into the empty p orbital, that also created a full octet structure. If atoms have the same octet status, then we would go on to look at charge accommodation. That is to say, based upon the electronegativity/size comparison, we'd look at which atom balances the charge better. In this example, when we compare nitrogen versus oxygen, because nitrogen and oxygen are in the same periodic row, we would use electronegativity to compare them. Nitrogen being less electronegative would balance that positive charge more stably than oxygen. So the far right contributor here is the most stable, or we could say the most significant contributor, and the structure with the oxygen positive is the second most stable. Okay. Again, we'll talk about this in a little bit more depth in a later video, solely devoted to resonance structure stability. All right, so if we're overall positive to begin with, we only need one arrow to go from our contributor to the next. And we want to recognize if we're starting in the middle or at the end of the system. Moving on to the next example, notice how here we're starting off overall negative. Okay, we have an overall negative charge. And when you have a negative charge, we're going to try to push that into an adjacent pi system. And we're going to require two arrows to go from one contributor to the next, whereas with the positive charge, we only required one arrow. So the very first push possible is to take the nitrogen's lone pair and delocalize that into the pi system. The nitrogen makes a pi bond to the adjacent carbon. That's what the first arrow communicates, and the second arrow is communicating that that carbon-carbon pi bond is breaking, and we leave a lone pair on that carbon. Then the rest of the structure would stay the same. Okay. Now tracking from this resonance structure here, that negative charge is adjacent to this pi system, so I can make a pi bond and then break the adjacent pi bond. Tracking with you, The first arrow is showing this pi bond forming here, and our second arrow is saying that the carbon-carbon pi bond is breaking, leaving this carbon negative. All right, and of course we still have the triple bond at that point. Now from this structure, we have our negative charge adjacent to the carbon-nitrogen triple bond. We can delocalize across the triple bond, because that's a lone pair atom adjacent to a pi system. I can make a pi bond between the two carbons and then break one of the pi bonds of the triple bond. Tracking with you, this would stay the same. Nitrogen still pi bonded there. We still have this carbon-carbon pi bond. The first arrow push is showing carbon-carbon pi bond forming here, a double bond. And the second arrow push is saying the triple bond is breaking, such that the carbon and nitrogen are only doubly bonded, and that terminal nitrogen atom is getting a lone pair. Kind of funky to think about that, but when we're delocalizing over a triple bond, you'll end up having pi bond on pi bond. Okay. All right, so in summary here, if we have a negative charge overall, we'll need two arrows to go from one contributor to the next. We need to make a pi bond and then break a pi bond. And here we just started at the very end of this system and pushed all the way across the system. All right, moving on to the next page, looking at this example, notice we have a negative and a positive. When you have both a positive and a negative, what we're going to do is move the negative towards the positive. Repeat that. When you have a positive and a negative, we'll move the negative towards the positive. And because we're moving a negative, two arrows would be required to draw the next contributor. I'm going to take that negative charge and move it into the adjacent pi system. I'm going to make a pi bond and then break the adjacent pi bond. The first arrow is showing a pi bond forming between these carbon atoms. The second arrow is showing that we're breaking that pi bond, leaving a lone pair on that carbon atom. And at this point, the carbon-nitrogen pi bond still is present there, and the nitrogen is still positively formal charged. Now that that negative is adjacent to the carbon-nitrogen pi system, I can make a pi bond with the adjacent carbon and then break the carbon-nitrogen pi bond. Tracking with you, that first arrow is showing a carbon-carbon pi bond forming here. And then I'm breaking the carbon-nitrogen pi bond, leaving the pi electron density on the nitrogen as a lone pair. And because that arrow terminated on the nitrogen, that's showing a neutralization of the positive charge. Now, it won't always be the case that when you have a positive and a negative, we fully neutralize, but in this example, we did. So if you have got a positive and a negative, we're going to delocalize the negative towards the positive. Two arrows are required to go from one contributor to the next. Now, for argument's sake, let's say that instead you had began here. Maybe this is the first structure that they gave you. There's no charges present, but notice how there's a lone pair atom connected to the pi system. If you're starting off overall neutral, no charges, but you've got a lone pair atom adjacent to the pi system, you would begin by delocalizing into the pi system. And that arrow push there in red would get you to this structure here. And at that point, you would just continue to resonate across the system. So notice whether we're moving a negative or we're moving a lone pair atom into a pi system, two arrows are required to go to the next contributor. Moving on to the next example. We're starting off with a structure, there's a negative and a positive. We're going to move the negative towards the positive, and two arrows will be required to go from one contributor to the next. So let's begin by taking the lone pair from the oxygen and moving that into the pi system. The first arrow is showing that the oxygen and carbon are pi bonding to one another. Oxygen is now neutral. Second arrow is showing that the carbon-carbon pi bond is breaking, and this carbon atom would then become negative. At that point, the nitrogens are still pi bonded to one another. That nitrogen's positive, and this nitrogen would still have a lone pair. Now that we're here, the negative charge is adjacent to the nitrogen-nitrogen pi system, so what I can do is I can make a pi bond between the carbon and nitrogen, and then break the nitrogen-nitrogen pi bond, leaving a lone pair on that top nitrogen. So tracking with you, the oxygen is still pi bonded to the carbon. Oxygen has two lone pairs. The first arrow is showing that the carbon and nitrogen are pi bonding here. Second arrow push is showing that the nitrogen-nitrogen pi bond is breaking and a lone pair is left on the nitrogen, which would then charge that nitrogen negatively. Now in this example, notice how the second arrow did not terminate on the nitrogen atom. That means the nitrogen atom is still positively charged here. Pausing, going back to the last example, we had both a negative and a positive, and there was overall a neutralization possible with the charges. That's because when we delocalized in that arrow push, notice how the second arrow terminated on the nitrogen, and that neutralized the positive charge and the negative. We did not neutralize that positive charge because our second arrow did not terminate on that positive nitrogen. It terminated on the topmost nitrogen, making it negative. And that's why I said with a positive and a negative, we don't always neutralize the charges. Now, if we had to gauge resonance structure stability here, notice that they're all full octet. Every atom in each structure is full octet. So we would then move on to charge accommodation, and we're looking at a negative charge. The negatives on a carbon here, negatives on an oxygen, negatives on a nitrogen. And with a negative charge, a more electronegative atom would balance that more stably. So if we had to argue, we'd probably say that the most stable contributor is this one here where the oxygen's negative, as it's more electronegative than the carbon and the nitrogen. The second most stable would be the one with the nitrogen negative. Nitrogen is more electronegative than the carbon. And of the three, the least stable would be having the carbon negative, as it's the least electronegative atom. Okay. But this page is really illustrating that when you have a positive and a negative, two arrows are required. We move the negative towards the positive. All right, moving on to page 7, looking at this example, notice how we're starting off with a negative and a positive, and specifically the carbon that's negative here is pi bonded. Before we get into this example, I want to make something abundantly clear, and that's that when we have an atom that's making a pi bond and has a lone pair, it's not always a delocalizable lone pair. So consider this with me. If I looked at this carbon of negative charge here, that lone pair is localized, meaning it's not existing in a p orbital, it would be existing in a hybridized orbital. That lone pair cannot resonate because there's no adjacent pi system. Okay, no separate pi system there. But let's say that we have maybe this example here. Okay. This example. This nitrogen is technically possessing a negative. Okay, negative has a lone pair. This one can delocalize here because there's this adjacent pi system and there's the ability to create a linearity. In order to be able to delocalize a lone pair on an atom that's already pi bonded, we have to be able to create a linearity because a triple bond would be formed as a result of that arrow push. So we have to be able to create a linearity. The negative would land on the carbon. So here that was delocalizable because of the adjacent pi system. This negative is not delocalizable here because there's no adjacent pi system. Now, that being said, if you have a lone pair atom within a ring, that lone pair should not be delocalizable if that lone pair atom is already making a pi bond. If we considered resonating that lone pair in this direction, that would be an invalid arrow push because that would charge the nitrogen positively, and the nitrogen making two pi bonds would have to be sp hybridized. But we can't have an sp hybrid atom within a 6-membered ring. We can't achieve 180-degree bond angles. For that reason, that arrow push is invalid. So let's make the rule that if you've got a lone pair atom making a pi bond already and it's in a ring, that should not be delocalizable. That lone pair would exist in a hybridized orbital separate from the pi system. And if we have a lone pair atom that's making a pi bond and there's no adjacent pi system, it cannot resonate. So coming back to our example here, this is a carbon with a lone pair that's already making a pi bond, but there's an adjacent pi bond there. And we have the ability to create a linearity. So tracking with you, we can delocalize the lone pair on that carbon, therefore that lone pair is in a p orbital. As I push that first arrow, I would show that the carbons are triply bonding to one another, and then I'm breaking the adjacent carbon-nitrogen pi bond, leaving the pi electrons there on the nitrogen as a lone pair. And then the oxygen is still pi bonded, possessing two lone pairs. So I want to summarize that again, and I'm not trying to beat a dead horse here, so to speak, but it's really important that we understand when we can and cannot resonate lone pairs on doubly bonded atoms. So if you've got a doubly bonded atom within a ring, okay, it's making a pi bond, has a lone pair, that lone pair will not be delocalizable. It's in a hybrid orbital. If you have a lone pair atom and there's no adjacent pi system, that lone pair atom cannot be delocalized. But we can delocalize a lone pair on a doubly bonded atom if there's an adjacent pi system, and the ability is there to create a linearity, as we showed in this example, and as we have here. All right. Now, the next thing that we can do is polarize this polarized pi system. When you have a polarized pi system like a carbon-oxygen pi bond or a carbon-nitrogen pi bond, we can take the electrons in that pi bond and shift them onto the more electronegative atom. As a result of that arrow push, the oxygen would be gaining an extra lone pair, taking on a formal negative charge, and the carbon gave up electrons. It would become positive. So we can polarize a polarized pi system. All right, then from there, notice how the nitrogen is now directly connected to the carbon, a positive charge. The nitrogen could resonate into the empty p orbital and make a pi bond with the carbon. Doing so would charge the nitrogen positively, and that would be the last resonance structure possible. All right. Now, this arrow push, to clarify, is kind of the arrow push that we looked at earlier. Okay, earlier we showed like a C double bond O. Now we could polarize that pi system, putting a lone pair on the oxygen, and that would make the carbon positive. Whether the C double bond O is charged positively or if it's neutral, we still have that ability to polarize the pi system. All right. Now, if any of that was kind of tricky to follow, I recommend going back and watching the portion that we talked about here. It is a little bit tricky to delineate the scenario with lone pair atoms that are already pi bonded resonating. So I want you to get that down. Now, to recap, earlier we showed that if you have a lone pair atom that's visually singly bonded and adjacent to a pi system, that could definitely delocalize its lone pair. And that's true whether it's a lone pair atom that's visually singly bonded within a ring or outside of a ring. This nitrogen atom here, because it's visually singly bonded and adjacent to the pi system, could delocalize its lone pair. The lone pair would be in a p orbital, and this lone pair would also be in a p orbital. But if you're within a ring and you're a lone pair atom, already pi bonded, that lone pair cannot delocalize. It would be a localized lone pair. All right, looking at this next example, we have NH2 bonded to a C triple bond N. We're recognizing that we're overall neutral to begin with, so any resonance should create a positive and a negative charge. I'm going to move that lone pair into that pi system. Lone pair atom adjacent to a pi system, I'm going to make a pi bond between the nitrogen and the carbon, and then break one of the pi bonds of the triple bond. The first arrow is showing that the nitrogen and carbon are pi bonding. The second arrow push is showing that we're breaking one of the pi bonds of the triple bond, leaving a lone pair on the nitrogen atom. That would charge that terminal nitrogen negatively, and because the nitrogen of the NH2 portion gave up electrons, it would become positive. All right. Moving on to the last example here, we're starting off overall positive. Therefore, only one arrow should be required to go to the next contributor. And because I have a polarized pi system here, difference in electronegativity between the carbon and oxygen is present, which is what makes it polarized. I can simply polarize that pi system, going from the middle of the bond to the oxygen atom. That would leave a lone pair on the oxygen, making it neutral, but then that would charge the carbon positively. From there, carbon a positive charge is adjacent to that pi system, so what I can do is I can go from bond to bond, shifting the pi electron density over and putting the positive charge at that terminal carbon, that pi bond. At that point, we're done with resonance because there's no more pi electrons or lone pairs to push towards that positive. Notice how here this carbon atom's sp3, so there's no pi density in that direction to move towards the positive. All right. Moving on to the next example here, we're starting off with an overall negative structure, so 2 arrows are required to go to the next contributor. Notice here that we have the negative adjacent to the C double bond O, and it's adjacent to the carbon-carbon triple bond, and we could resonate over both. First, I might conceptualize of resonating over the C double bond O. I could make a pi bond here and break a pi bond. That means that the triple bond is still intact, so let's go ahead and draw that. We'll preserve the triple bond. The first arrow is showing that we're forming a carbon-carbon pi bond here, and the second arrow is showing that the carbon-oxygen pi bond is breaking, and we're leaving a lone pair on that oxygen, charging it negatively. Now from that starting structure, I could alternatively do a red arrow push. Okay. The blue arrow push created this structure. Let's now track a red arrow push. And in the red arrow push, we'll conceptualize of moving into the triple bond. The carbon that's negative, we can use that lone pair to make a pi bond, and then we can break one of the pi bonds of the triple bond. So that would create this far right structure. Let's track that the first arrow is showing that these carbons are pi bonding to one another. There's a double bond there, and then breaking one of the pi bonds of the triple bond, leaving those carbons that were triply bonded now doubly bonded, and the pi electrons from the triple bond are being left on that carbon atom here, charging it negatively. But as I do that red arrow push, let's acknowledge that the C double bond O is still intact. Okay. So here we were starting in the middle of the pi system, and therefore I had to use different arrow pushes to shift to the left, making this structure on the far right. And in blue, I delocalized over the C double bond O, creating that contributor. All right. Let's now look at this example here. We're starting off overall positive. So what we should do is try to move towards that positive charge. Now, notice that we have lone pair atoms, 2 lone pair atoms specifically, adjacent to that carbon-nitrogen pi bond. What I could do is this blue arrow push, where I'd make a pi bond between the oxygen and the carbon, and then I break the carbon-nitrogen pi bond. As a result of that push, the first arrow is showing that the oxygen is pi bonding to the carbon, and the second arrow push is showing that the nitrogen is getting the electrons from the carbon-nitrogen pi bond, making the nitrogen neutral. The next thing that I could do is maybe now delocalize a lone pair from this oxygen into that pi system. I can make a pi bond and then break that carbon-oxygen pi bond. As a result of that flow, the first arrow is communicating that the oxygen is pi bonding to the carbon. That makes this oxygen charged positively. And the second arrow is showing that the carbon-oxygen pi bond is breaking, leaving a lone pair on that oxygen, making it neutral. Okay, so essentially we were able to delocalize each of those lone pairs separately into that pi system to alleviate the charge on the nitrogen. Then the very last structure that we could create is doing this push here in green. I could simply polarize that polarized pi system. I can take the pi density and move it onto the oxygen, creating another lone pair, making that oxygen neutral. But as a result of that push, that would leave the carbon positive. Okay, that is a valid resonance structure. With a polarized pi system, we can simply polarize it, moving on to the more electronegative atom, and that would make the carbon positive. All right. Now, we were overall positive, but we needed 2 arrows to describe the flow there. Because we were making a pi bond and then breaking a pi bond, we were moving the lone pair. Right? 2 arrows are required there as well. But when you're polarizing the polarized pi system, only 1 arrow is required. All right, we are going to do one more example here. Looking at the structure, we're starting overall positive, and I'm detecting that I'm in the middle of the pi system. So what I could do initially, perhaps, is go from pi bond to the adjacent bond, from bond to bond. That red arrow push would create a structure here. Thinking about what's staying the same, at the top, the nitrogen still has its lone pair. We have that carbon-carbon pi bond, but then pi density is shifting over to pi bond those carbons, and the positive charge is now at the very end of the system at that terminal carbon. That carbon becomes positive because this carbon gave up a share in electron density as the pi system moved over. And because we're overall positive, only 1 arrow was required to go to the next contributor. Now, because we started in the middle, an alternative push that I could do in blue here is going from bond to bond, moving this pi bond over. Let's track it that if I did that blue arrow push, the pi bond at the bottom of the structure is still intact there. But then with the blue arrow push, these carbons are pi bonding to one another, and that would make this carbon now charged positively. Then one final structure is possible. In green here, what I could do is I could take the lone pair from the nitrogen atom and make a pi bond with the adjacent carbocation, given that the nitrogen is directly bonded. So the nitrogen and carbon are pi bonding. Nitrogen takes on that positive formal charge, and the rest of the structure then stays the same. Okay. Now in the next video, we'll talk more about resonance structure stability and ranking those. Before we do so, let's acknowledge that these contributors here our incomplete octet because we have a carbon of positive charge for each of them. But when the nitrogen resonates into that empty p orbital, that creates a full octet structure, and accordingly, this far right contributor in this instance would be the most stable. Having full octets is ideal, makes it more stable than having incomplete octets. All right. Now, each of these examples are exam caliber examples. I want to summarize kind of what we've detailed here. We want to track and see if we're starting in the middle of the system or at the end, right? And if we're in the middle, we need to acknowledge that we could format it with different arrow pushes to show the flow. Now, when you're overall positive, only one arrow is required to go to the next contributor. I could move to the adjacent, I could go from bond to bond, moving the positive across the system, or I could delocalize the lone pair from the oxygen into the empty p orbital. But one arrow was required to go to the next contributor. If you're overall negative, we would want to move that negative into an adjacent pi system, and 2 arrows are required to move that negative across the pi system. We need to make a pi bond and break a pi bond. When you have a positive and a negative, we want to move the negative towards the positive because electrons move from high density to low density. And sometimes we'd be able to neutralize the positive and the negative, but that's not always going to be the case. But we would neutralize the positive and the negative if we could terminate our arrow on the charged positive atom. Okay, here we were overall positive. We had positive and a negative. We move the negative towards the positive. 2 arrows are required to go to the next contributor. We then detailed situations where lone pair atoms would have a pi bond already and when we would delocalize versus when we would not. And here we also illustrated how we could polarize a polarized pi system. If you were overall neutral, no charges, and you have a lone pair atom adjacent to a pi system, whether that's a double bond or a triple bond, we should be able to delocalize into the pi system. That would naturally create a positive and a negative charge as a result of that movement. And in this example here, we started off overall positive, kind of at the end of the pi system, and we could begin by polarizing that pi system and then moving the positive across. In this example, we were overall negative, so 2 arrows was required to go to the next contributor, and we were in the middle of the system, so we could do the blue arrow push resonating to the right or the red arrow push resonating to the left. In this example, we had a positive charge, and we specifically had lone pair atoms adjacent to that pi system. So I could use 2 arrows to show that oxygen taking on the positive charge, or in red here, 2 arrows to show this oxygen taking on the positive charge. Now, earlier I said only 1 arrow is required when we're overall positive. An exception to that is when you have the lone pair atom attached to the pi system that's positive, right? I think that's important clarification. In this last example, we were starting in the middle of the pi system, so we could move in either direction, and 1 arrow was required to go from one contributor to the next. All right. Now, the more resonance examples you do, the more you're going to get comfortable with arrow pushing. This is a really important skill. And remember that we delocalize lone pairs or pi electrons towards pi systems or atoms with empty p orbitals.